Welcome to circular motion. Here we have a simulation with a turntable. There are two objects on that turntable and they are at different distances from the centre. You can see the vectors of acceleration towards the centre of the circle and the vectors of velocity at 90 degrees pointing in the instantaneous direction of travel. Both of these vectors are constantly changing direction one moment to the next. The object further away from the centre of the circle has a much larger acceleration creating this movement. That means it needs a larger force. And the force that causes something to move in a circle is called the centripetal force. So further out toward the edges, we need a larger centripetal force than near the centre. Notice as well that the size of the velocity vector stays constant as the objects rotate, but the direction is constantly changing. If we are going to describe the motion of objects moving in this way, then really we need a variable that isn't going to be constantly changing direction all the time. In the past, we've been talking about linear motion, and we had several variables to describe this type of motion. We had displacement, measured in meters. We had velocity, which is the rate of change of displacement, measured in meters per second. And we have acceleration, which is the rate of change of velocity, measured in meters per second squared. Now that we're going to discuss circular motion, there are equivalent terms. So instead of displacement, we have angular displacement, the angle through which the object has rotated, measured in radians. Note that 2 pi radians is equal to 360 degrees. Instead of velocity, we now have angular velocity, which is the rate of change of angular displacement, measured in radians per second. And instead of acceleration, we now have angular acceleration, which is the rate of change of angular velocity, measured in radians per second squared. So far, the only differences are the symbols, the slight change to the name, and the fact that instead of meters, it's radians. But the relationship between these variables and these variables is the same. The rate of change of angular displacement is angular velocity, and the rate of change of angular velocity is angular acceleration. Just like the rate of change of displacement is velocity, and the rate of change of velocity is acceleration. If we look at the simulation, when an object moves around the outside of a circle, it maintains the same radius at all times. We can describe the movement either by using the angle through which it's moved or the displacement along the outside of the circle. These three terms are linked. You can express it either as angular displacement or as linear displacement. These two terms are connected. We can substitute this equation in here. When an object is moving in a circle, it is the angle and the displacement that changes. The radius is constant, which means that when we substitute this equation in for this term, we get notice the similar term here, which becomes and if we substitute this in here, we get and notice again which gives us this. If we have a look at this equation in a little more detail, then we can get some more information as well. The angular velocity is the change in angle divided by the change in time. If the change in angle is one complete circle, then that would be 2 pi radians. And the definition of the time it takes to complete one cycle is known as the time period. So this is true as well. And of course, time period and frequency are inverses of each other, so we can also write this. Note that angular velocity is sometimes called angular frequency, and this is why. The centripetal acceleration, that is the acceleration that keeps the object moving in a circle, is defined as v squared over r. With some algebraic manipulation, we can turn this into multiplied by r, v over r is the angular velocity. Another equation that you'll be familiar with comes from Newton's second law, which allows us to calculate the centripetal force. With all of these equations and the ability to link them to linear motion, we can fully describe the motion of an object travelling in a circle.